So anyways, as I said, I'm probably not going to call the thing that we're doing SBI or simulator-based inference. I'm going to go likelihood-free inference because that's the way that I was brought up. So bear with it. So our sort of the first part of this, not anymore 3-hour lectures, so about 2 hours and 45 minutes, I guess. So I guess about 45 minutes, we're gonna go over the concepts, the basics of likelihood-free inference, and namely 3 different methods we're going to concentrate on that we're going to go also apply using ELFI, engine for likelihood-free inference, to deal with some problems later on, some inference problems. So the basic building blocks of likelihood-free inference, we're going to go sampling-based ELFI methods, namely approximate Bayesian computation methods. So okay. Yeah, I'm going to do it the old-fashioned way, and in the end, I'm going to do like smashing mic drop. So bear with me. Okay, so we're going to start with sampling-based methods. So the first likelihood-free inference methods that really like broke the bank like 20 years ago, well, 15 years ago. So rejection ABC method, then go over to the methods that try to do a bit smarter things than very computationally intensive rejection sampling ABC. And then in the end, we're going to go over a couple of active learning methods. So active learning is going to be a thing where you're going to try to choose where to find information about the parameter space instead of blindly going all over the parameter space, because that's not very efficient when you're trying to infer something. And the 2/3 of the lectures are going to be about ELFI. So, or let's say that 1/3 is going to be about ELFI, and then the 1/3 is about basically applying ELFI to a problem. But if you're familiar with any other likelihood-free inference software, feel free to sort of complete the assignment using that. So I should be quite aware of what the other software packages do. So I should be able to advise you also with other packages. So in the tutorial that's in Google Colab that apparently you can't access right now. Okay, we're gonna sort that out. We're gonna go over like the basic model building methods and tools and sort of tricks that we're going to do in ELFI, and do some exploration of the models, and then use those built inference or inference models that we're going to build, and we're going to throw them at a couple of different inference methods that we have applied in. So simulation-based inference. Oh, this is the second time that I use simulation-based inference. So after that, it's going to be likelihood-free inference. So as we are having like enormous amounts of computation power, so that the mathematical modelers have had great time within the last about 20 years. So they've been like really been able to model real world in a detail that was not possible decades ago. So we've been able to simulate different environments with ever increasing detail. And sometimes when we have this possibility of simulating the real world, that opens up the possibility of doing in silico experiments. So we can run the simulators instead of trying out drugs with people, at least on the first stage. if we model the people as simulators, or how the drugs are affecting people as simulators, then we can use those simulators to gain knowledge about what and how the real world is behaving in under certain situations. And the complexity of the realistic simulators, that comes with some problems. And the main problem, if you want to do inference, is that you cannot access the likelihood function anymore. So the likelihood function is obviously the workhorse of all statistical inference, because that ties the parameter values, how likely they are, conditioned on the observations. We lose that. So a couple of examples of where we use simulators to do inference, where we're not really doing MA2 model, moving average of order 2 model, but that's a example where the likelihood function does not exist. And it's a very simple model, but still you cannot construct, at least analytically, the likelihood function. This is a real example of a real-world simulator where we simulate bacterial strain transmissions in daycare centers with children. So it's a cross-sectional data from daycare centers from a stochastic SIS model. And we have a continuous time Markov process with a set of transmission probabilities, definitions of variables there, but it's constructed from these different building blocks. And we cannot access the likelihood function, but we can simulate data with different parameter values. And the data in this case would be these kinds of binary matrices where you have different strains and individuals are children here in different daycare centers. So your simulated data can be information of which child in which daycare carries which strain of bacteria. And then you can model how these strains and how the children are infecting each other, either within that daycare or between daycare centers. So the data can be looking very, very, very different than in different applications. Then a real example that we are playing around in the University of Oslo is a personalized medicine example. So and also like drug discovery and modeling of treatments is a big area of likelihood-free inference, because you can build these very detailed simulators nowadays. So, and that gives you access on how the response of the patient to the treatment, what kind of response he or she is going to have when imposed with some chemotherapy or drug combination. Then you can experiment with different drug combinations. So it's a fairly complicated model. It's a multi-stage partial differential equation model that models all these different pieces. And then we get out basically models of how the cancerous cells and the vessels and the drugs, how they're evolving in the tissue. And you get all these kinds of like patient-specific information out from the simulator. And here on the top level, there's the sort of the density of cancerous cells, for example, in a biopsy. And when you start treatment on a patient on a time 0, and then you get another treatment period at week 3 and 6 and 9. And you see that we can investigate that when you set this combination of drugs, that the density of the cancerous cells, for example, is first going down a bit, but then it goes up until the 3-week treatment period. So the next vertical line there is the 3-week mark, and then it goes down again because some combination of drug treatment is given to the patient. And what you want to see in this kind of personal medicine example is that you want to simulate that this combination of drugs is killing the cancer cells, but not killing the patient. So we're going to start with the very basics. So what is a definition of a simulator? For us, it's just a computer program that generates stochastic data given a set of parameters. There could be some other extra elements involved here, like, because we're simulated with computers, there could be setting of the seed so that everything is reproducible in simulators and something like that. But that's not really necessary. So, but the essence is that you have input parameters and you have stochastic output. And when we're doing likelihood-free inference, we assume that we don't know the form of the function. So that when you have the parameters theta, all you can do is query the simulator and you get some kind of response. And that's how you get information about it. So, okay, apparently the animations are thinking a bit every now and then. It's supposed to be smooth as butter, but anyways, I wouldn't call them black box simulators because we're doing everything in Bayesian way. And we do have information about the parameters themselves. And usually you are the ones, if you're doing likelihood-free inference, that you have actually implemented the simulator. So even if you don't have the analytical structure of the likelihood, it doesn't mean that you wouldn't know anything about the simulator, and that information you can use when. So not black box, but let's call it a gray box, the simulators. You know something, and you can use that to build priors, for example. So, and the data, we don't impose any regulations or rules on what kind of data the simulator outputs. It can be single time series, like in moving average model, sets of independent data, images, or distributions of data points. And so basically it can be anything, but we do need to transform the data for certain methods when we're doing the inference so that we can actually carry out the inference. So the methods themselves have some restrictions of what kind of data you can feed into them, obviously. So inference. So we observe data, want to infer parameters. Clear. It's the main workhorse is the likelihood function. So you have the observation model feeding observed data, and you look at that as a function of theta. And then you do different things. And the two approaches that people use are either the maximum likelihood method, so maximization of the parameters, or using Bayesian approach, so trying to find the posterior distribution of the parameters given the data. And in likelihood-free inference, we don't assume that the likelihood function is a vector. So how are we going to do the inference without likelihood? So the idea is that because we have the capability to draw data from the simulator, giving any inputs that we wish to give to the simulator, we assume that the true parameters produce, well, there's a question of what true means, but anyway, better parameters or more probable parameters produce data that is closer to the observed data. It's a reasonable assumption, but it does come mathematically comes with some questions. So what is like similar data? So we need some kind of mechanism to sort of compare data sets. So we need some way of saying that this data set is better than the other data set. And in approximate Bayesian computation, we can approximate the posterior distribution based on this idea that we replace the likelihood function, the p of x not given theta, with the integral of what's the probability that you have generated data that is close enough to the observed data. So the region omega contains of the data points that are in some sense close enough to the observed data. That you need the distance metric, so the D. And that defines the acceptance region that we have in classic likelihood-free inference methods. What kind of distance metric is reasonable? That really depends on your simulator and the sort of the situation that you're trying to infer parameters in. So if you have images or you have time series data, the distance metric is going to be very different in these cases. Or you have some sort of bacterial strain composition or whatever not. So you need different distance metrics based on the data. So if you have distances like we have, or distributions as we do have in our assignment, you may want to use quantiles or Wasserstein distance to compare data sets. So two distributions to each other. One of them is the observed one, and the other ones are the generated one, artificial data sets. And one of the biggest problems when we run these likelihood-free inference methods that are based in simulators, that is the dimensionality. So in high dimensions, it's increasingly difficult to generate data that's similar to the observed data, because high dimensional spaces are empty spaces. So there's the curse of dimensionality aspect that the computation power grows, the required computation power grows exponentially very fast with the increase in dimension. And the standard approach currently, I say currently still, is to use summary statistics. So way to decrease the dimensionality of data using a functional transformation. So calculating summaries of the data. So instead of comparing artificial and observed data points, you compare the summarized data and summarized observed data points. And you could think of this as a metric, well, not the metric, but discrepancy between observed data and artificial data. So you could think about it as a function of rho. That's sometimes convenient. But the problem is that because we have only simulator, so we don't have the likelihood function. So we don't have really any method on constructing sufficient statistics. So they don't usually exist. So what are we to do? It's pretty much an open problem. Sorry, spoiler. But what we do usually is that we use bespoke summary statistics. So we use either the domain expertise, because people who have dealt with cancer simulators or whatnot, they have unique aspects on what kind of features of the data is important for the outcome, for example. The sort of the computational approach is exploration of the simulators, because you can always simulate data. If it's not too expensive, you can simulate lots and lots of data, and you can explore how the summary statistics behave under circumstances. And you can also sort of do the analysis again using different summary statistics. Then it sort of becomes a bit like a model comparison problem. So you can solve the same problem using different summary statistics, and you get an idea of how sensitive the inference protocol is regarding the summary statistics. And then always the problem is that the reason that why we're using summary statistics is to decrease the dimension. So you don't want to throw too many summary statistics to the inference problem, because then you're facing the same problem, that you increase the dimension of the summary statistics and you can't do it in inference again. So they are these automatic selection constructing approaches for summary statistics, dealing with summary statistics. So they can, for example, work in a way that you throw a lot of summary statistics. So you construct a set of summary statistics, huge sets of summary statistics, and then it automatically does feature selection based on those summary statistics, based on the simulations that you do. So that's a sort of a valid approach on selecting summary statistics. So when you put all this together, you get a rejection ABC. So pretty much the first likelihood-free inference method of a new wave. So the algorithm itself is really, really simple. It's just a couple of lines of code. So what you're doing is that you're sampling from the prior, and those prior samples you forward propagate using the simulator, and you check whether or not those forward propagated samples are close enough to the observed data. And if they are close enough, based on some threshold, you keep those samples. So we have our prior, we have a simulator with some acceptance region, and then we have an approximate posterior distribution. Smooth like butter. Give it a minute. It's going to be worth it. So you draw samples from the prior, you keep only the red samples, so the samples that land into the acceptance region, and then you start building up the posterior probability distribution, or the approximate posterior probability distribution. And to get sort of detailed enough posterior distribution, that really depends on the dimensionality of the problem. So in real life problems, you probably want to run it longer than we're running it here. So that the alternative approach for rejection sampling ABC would be, if you have, for example, no idea what's a reasonable threshold. So other approach is to sample lots. If computation power is not a big problem for you, if you have access to the supercomputers of your university, you might as well just simulate a bunch. And then if you keep a certain quantile, if you keep like the, let's say, 1% or 0.1% of the samples with the smallest distances, you get an idea of the threshold level that's sort of working. The problem is that you sort of you fix pre-hand, like the pre-inference, you fix the number of simulations that you're running, so you know how long it's going to take, and in the end you get something out. But if you're running it with a fixed threshold, you don't really know how long you are running the algorithm so that you get enough samples from the posterior distribution. Yeah, so the problem with rejection ABC is obviously that it samples from the prior, and that is never a fantastic idea in Bayesian inference. So it can be if your prior is very narrow. If you have lots and lots of prior information, then you can just use prior information in your posterior sampling, but that's not usually the case, especially when you're dealing with simulators and everything is a bit vague. So usually your priors may not be that tight. So there are different approaches on dealing with this, and sort of the first and simplest ones are based on imported sampling. So sequential Monte Carlo methods, they sequentially construct important sampling distributions so that you gradually get closer and closer to the posterior distribution. So your sampling distribution gets closer and closer to the posterior distribution, and that is much more efficient than sampling from the prior. But basically, SMC-ABC is nothing but running rejection ABC multiple rounds. So you start with the first round being exactly rejection ABC. What you do is that when you have your set of samples, you compute a empirical covariance function for that data set. And you use that, well, a certain transformation, so it can be shown that it's optimal to multiply it with 2. You can find the proof in literature for that. So you set a new proposal density on propagating the samples from one iteration round to another. So you had your first loose threshold, epsilon1. Then you go on by setting a tighter threshold. And you have your sets of poor posterior samples. And what you do is that you take your empirical proposal density and you use that to propagate all of the samples. So a Gaussian proposal, you just jiggle a bit the samples. You know that they are closer to the real posterior distribution than prior. And then you sample again on those points. And in essence, you just repeat this multiple times. The only thing is that you need to calculate the empirical covariance function, and then you have that weight calculation. So the weight calculation is just the importance weight. So in essence, we calculate the probability that for each of the particles that we would move from any of the old particles to the new particles. And that's in essence what's that. And we have SMC-ABC tutorial with ELFI. Okay, so things that go wrong. So if you're blindly just throwing out summary statistics to the problem, you're not helping. You're just basically decreasing the dimension, but you're not selecting any of the interesting features. So that's one problem, but the other one is that you decrease the dimension too much. So you're not solving the same problem, or even approximately the same problem that you set out to solve, the inference of the parameters of the true simulator, if you decrease the dimension too much. So sometimes you can, but pretty often you cannot decrease the dimension of an image to a single number. You're not an astrophysicist. Other way is that you didn't decrease the dimension enough. So your dimension is still too large and your method is not working because of that. If you're also blindly constructing summary statistics, they can be correlated with each other. And that's a problem because then you have redundant summary statistics. So it's, you're aiming to constructing independent summary statistics. Basically, that's the most efficient way of doing that. Then one issue that should always be a part of sort of a likelihood-free inference pre-exploration step is that you want to find out what is the scale of your summary statistics. So if you choose summary statistics that have like wildly different scales, the ones that have bigger scales and like large variability, they're going to dominate the distance metric. The ones that have smaller scales, they may not contribute to the inference part at all. And this is a thing that's pretty common, but it's also pretty easy to solve because you have distance metrics. If you have a Euclidean distance metric, you can set a weighted Euclidean, for example. So you can weight the summary statistics, scale them down so that they are on a similar scale, so that your ELFI methods are efficient. So there's a book that contains like most of the material that was written until 2016 called Handbook of Approximate Bayesian Computation. If you're interested, at least individual chapters of that are available online. And they have a nice collection of real world simulators as well in the end. So we move on from the sampling-based methods to the surrogate-based methods. So instead of trying to sample from the approximate posterior distribution directly, we can instead of construct models and fit models to the parts of the simulator that we can deal with. And the simplest one is the synthetic likelihood. So at any given parameter value, theta, because we can draw a simulation from that, we can draw many simulations from that same parameter value, and then you can calculate the empirical Gaussian approximation to the simulator output at that parameter value. And that obviously, if we can do that, we can do that, and we can calculate the likelihood function, because then if the model is Gaussian at that point, we can fit the observed value to that. So here's a sort of a sweep over the parameter values, and then on the second plot, you see the values that were sampled in that particular parameter value. And we fit a Gaussian to that histogram, and we get an estimate of the likelihood function at each of the points. So that results So when you evaluate the Gaussian empirical estimate at the observed value, you get an estimate of the likelihood function. And obviously with that likelihood function, you can use that with any of the sort of traditional sampling methods. So you can throw that synthetic likelihoods at the MC-MC. So each of the proposals, you just construct like a synthetic likelihood, and then you can calculate the acceptance probability at that point. But the problem with synthetic likelihood is that it's hardly very efficient. So at each of the parameter values, you are drawing many queries of the simulator. Let's say that you need at least 30 calls of the simulator at each of the parameter values that you're exploring. So the number of simulators that you need to draw, it increases extremely fast. So there are clever surrogate methods. We're going to concentrate on ELFI. it's Bayesian optimization for likelihood, for instance, but basically it's a framework of fitting a surrogate model to the regression model to the parameters versus the distance function. So we fit in the standard, we fit a Gaussian process to the pairs of parameters and the distances that we evaluated at that point. And you had Gaussian processes yesterday, right? Good. So when you have fitted the Gaussian process to the evidence set, so the evidence set is the point, the parameter values where you query the simulator and the queried distances and realized distances, and you fit a Gaussian process to that, and from that Gaussian process surrogates, so the probabilistic model for the distance, you can calculate the likelihood function by just integrating or using the Gaussian CDF until some sort of ABC threshold value epsilon. So, and then you end up with a posterior distribution. And GPU surrogates, because they're probabilistic surrogates, they're fantastic in the sense that they give us information about also the other parameter values that we have not yet queried the simulator from. So we can interpolate what would be the discrepancy at values, at parameter values that we haven't seen yet. And we can use this information to deduce where we should sample the simulator next. And this is called active learning. So it's an adaptive strategy of selecting the parameter, the query points for the simulator. And it's usually based on some sort of optimization, depending on, you can optimize different things, but you can try to find optimal points where to query the simulator next. So the two approaches, for example, could be that in the original ELFI, the approach that they wrote down is that you try to minimize the distance. It sort of makes sense based on the idea that you think that true parameter values generated more likely or more closer data closer to the observed data than the non-true parameter values. So based on that, it's pretty good. But from the active learning point of view, they're not really optimal because they're not taking into account that you're trying to get the surrogates as good as possible, as fast as possible. So you can also, instead of minimizing distance, you can select where to query the simulator next based on the points that you expect to give the most information about the posterior distribution. But the active learning cycle is that, you update your GP based on new evidence points, maybe do some hyperparameter optimization that probably was mentioned yesterday. Gaussian processes are defined by these latent parameters, hyperparameters, and you can optimize them based on the evidence. So, querying information about the simulator using GP that sort of connects the parameter values and their responses probabilistically, it decreases dramatically the number of simulator queries that we need to get a good estimates of the posterior distribution. Pretty quickly in these simple examples, which is the 10 or so points, we get pretty good estimates of the simulator, depending on, obviously, the variability of the data and so on. And then from the fitted GP surrogate, by calculating Gaussian CDFs, you can get point-wise estimates of the likelihood function, which you can then use to get a posterior distribution. Yeah. So, as mentioned, trying to find the parameter values that minimize the distance are not necessarily the most efficient ways of querying the parameter space when the focus is on finding the posterior distribution instead of the minimum discrepancy. So there's a paper by Marko Järvenpää that goes over a few quite efficient learning methods. We look what they are. So the LCBSC, the lower confidence bound selection criterion, that's very good. I mean, it's efficient rule of trying to find the minimum point of the discrepancy. But then there are three other methods that are related to each other that are computationally much more demanding to calculate, and you use these acquisition functions, these active learning strategies, but they tend to converge faster. So it can sometimes, depending on how patiently demanding it is query simulator, it can be still a good idea to use resources to find the best points where the query, so that you can minimize the queries. For example, in the cancer simulator model, one treatment period simulation is about 15 minutes. So if you need thousands of points, you're talking about lots of computation power that you need. And these are not necessarily used in real patient treatments yet, but I'd assume that if they would be, at some point, the time can be of the essence. So you want to find the patient-specific parameter values quickly, because if you're talking about cancer treatment, you want to act fast. You don't want to crunch your supercomputer for a month if the treatment period is supposed to be 3 weeks, for example. So the lower confidence bound selecting criteria, a two-part process. First, we optimize the moments of the Gaussian process, basically. So try to find a point where that's sort of most probably smallest. Then you take that point and then you perturbate it, the Gaussian, the truncated Gaussian, because you can have an optimization region. So you can have, you have bounds for the parameter values. Then you perturbate the sort of the minimum point that you find, because that would be purely exploitation of the current Gaussian process fit. But then you want to explore the parameter space a bit, so you perturbate the value a bit so that you can put, if lucky, you could find a non-local maximum if you're stuck in a local maximum. So jiggle a bit where you sample the query of the simulator next time. The maximum variance acquisition method. So each of these are based on a Gaussian process surrogate, and that means that you can calculate the posterior estimate by integrating the Gaussian process point-wise up to a ABC threshold, epsilon. So your posterior estimate is going to have variance because you have probabilistic surrogate for the parameter values and the distance. So your posterior distribution also is going to be probabilistic. And you want to find the point where that uncertainty about the posterior curve is maximal. So you want to find a point where you could get more information. So decrease the variance the most. That's the idea. So instead of maximizing that point, you can turn that posterior distribution variance into density. So you need to normalize that posterior variance function, and then you can sample that. It can give close, very similar points to the maximization of the variance function, or not, depending on the shape of the posterior distribution. So taking basically the mean instead of a random next value instead of the maximum next value. And then arguably the most efficient method in trying to find the most informative method is to find the parameter value that the expectation of querying at that point gives you the most information about the posterior distribution. And that's the drawback of this method is that it's quite difficult to calculate, because you need to integrate the important sampling weights omega I there, that we're not going to go there because the equation for that is, you can find it from the original reference or looking at ELFI code. But if the simulator is computationally very intensive, it may be worthwhile of trying to really find out what are the points that brings the most information. So, because in Bayesian inference, usually what you want, an object that you can actually do something with, is not the posterior curve, but you want samples from the posterior distribution. So with the surrogate methods, you need to sample from that, and you can use a whatever sampling method for a arbitrary curve you want. MC, Hamiltonian Monte Carlo methods, if your dimension is a bit larger. Our software package comes with Metropolis Hastings and no U-turn sampler that you can try to draw a posterior sample. And after you do the inference, after you have a posterior sample, you interpret the results. So, but this is pretty much what you would do in Bayesian inference anyway. So you had your Bayesian workflow presentation earlier this week, right? So all the things that were mentioned there probably apply here as well. So it's still Bayesian inference, but we just have to do some extra tricks. And those extra tricks that we have to do dealing with summary statistics and metrics, they do introduce extra uncertainty and error to our inference. So we really have to be like extra careful of looking at the results that we get, so that there is nothing funny going on. And sometimes the problem is that you can't separate the error source. So that's why you usually, when the model building phase, you usually want to look at all the bits and pieces separately, even before doing the inference. And then you do that again after carrying out the inference. And then if everything has failed, then you can redo stuff. You can fit either a different simulator, you can switch around summary statistics, use different distance metrics. And usually if everything runs fine, I mean, if the nut sampler doesn't give you error messages, you're probably fine. Or the Metropolis Hastings have converged, then you're probably fine. But if something funny has happened, you will probably get error messages from the samplers. And these are the basic building blocks that we're looking at the ELFI tutorial. And I was thinking that we can probably have first break now, and we can set the Colab documentation, the sharing privileges on. So how long breaks have you held here? My choice. 2.5 hours. 12 minutes, bathroom break. That's fine. Okay. So let's meet 20 past. So I was thinking that after we go through the tutorial in ELFI, I was thinking about having another break for people who want to have another break, and some people may want to start doing the assignments right away, but at least there's a possibility of having a break. Sounds good? Good. So yeah, let's see how long this is going to take. Usually it's about 40 minutes, so I think we're on a schedule. So the assignment is at the end of the tutorial, and we're going to go over that when we get there. So this is going to be a tutorial on ELFI. There are other likelihood for inference packages available in Python and in R. It may be better just to stick to ELFI, but if you are adamant on trying out other packages, that's fine as well. But they're not in the Colab environment. I had a link to a Gitter chat room where you could ask questions about the assignment, but because there apparently is the Slack channel, so the Gitter link is redundant and you don't have to bother with that. But if you want to ask questions later on, you can use the link to ask questions from there as well. Anyways, so let's get started. So ELFI, it's a I didn't have the in my usual info slides in ELFI, but it's an engine for likelihood for inference. It was developed at Aalto University, Helsinki University, Oslo University, and Edinburgh University. Currently, I'm in charge of maintaining it, at least for the time being. It's an open source package, so you are free to contribute to it. It's really, really good. You get a lot of fame and fortune, not fortune part, but fame on contributing to it. So if you find annoying features or features that are lacking, you can raise issues in our GitHub if you want. It's in GitHub ELFI-dev, and it's the ELFI repo. There's also the zoo repo where you can find other interesting stuff that may or may not someday find its way to ELFI. There's settings here. Oh, that's just one. There's not a way of changing the font size of the whole notebook. Yeah, I could do that. That's a good idea. I know how Firefox works. Yeah. No. extra big cell block coming up. Okay. Where was I? Oh yeah. So ELFI, you can pip install it, or conda forge. You can conda install it if you wish, or run everything here in the OLAP. Some of the more computationally intensive features are not included in the Colab because it would take too long to just watch them run and our progress bar to progress. So some of the more intensive features are just sort of demoed in a very quick fashion. Oh, no. Okay. So first, include everything we require to run the code. Oh yeah, we didn't even pip install it yet. So first pip install it. It's going to give an error about it's related to Dask, but we're not using Dask here. So we do support a automatic parallelization of the methods that we're not going to really demo here on the Colab documentation, but there's a elfi.readthedocs.aio. I can send the link on Slack as well. That has a list of other features that are in ELFI that we're not going to go through in this tutorial. Call it. So don't mind about the error. But yeah, it's about Cloud Pickle, so it doesn't influence whatever we're doing here. So now we can go back and start our environments. So importing stuff. There's the seed setting there that's work for all the, well, I think it should work all the methods that we have for the that has random numbers, so that in principle you should get the same results that's in your own Colab up here. Okay, so we start with the model building in ELFI. Start with the moving average of order 2 model. So very, very simple model. And here we have some restrictions on how we are coding up a simulator in ELFI. So we have basically 2 keywords that you have to take into account. So otherwise, it's a regular Python function that you define, and it returns something. And if you want to sort of, if it's possible, you may want to use linear algebra and sort of matrix operations so that you can return multiple values at once by taking into account that T1 and T2 inputs can be vectors. So these, in principle, these have to be able to be NumPy arrays of any length. Then there's the keyword for the MA2 process, so the length of MA2 process, we could fix that, but so we have 2 fixed keywords that we need to set for ELFI. One is the batch size, and one is random state. So the batch size, that defines on how many values we are basically simulating at once for our inference method. So if you can use linear algebra to sort of speed things up without using, in a sense, for loops, so using calculations, you should do that because that's going to speed things up a lot. But anyways, you can set the batch size to default value 1 when you are making a method. And then the random state keyword that we can set up to none. So random state takes, because the ELFI engine takes care of the pseudo random number generation in itself. So we need to pass this generator state in each of the methods. It's just a keyword that you feed in, and that's only thing that it does is that, well, it gives an error if you don't have it, but you don't have to set it. But if you want to reproduce exactly the same results later on, you need to have it so that you can. So as all statistical inference software libraries, there's going to be a little of the shape broadcasting. So in our case, the sort of the form for the data, there can be exceptions to this, obviously, but usually it's a good idea to output data as NumPy arrays. NumPy arrays so that your batches are in first rows. They are like row dimension is going to be batches, so they're going to be usually independent realizations of the simulator in batches. It doesn't actually need to be, but usually that's a good idea to have it so that you have less room for error. So here in MA2 model, it's just adding up and multiplying, so you can do it very quickly using linear algebra. So you take the normal distributed W's with different lags, multiply them with theta 1 and theta 2 that are marked T1 and T2, and add them up and return that. So the random number generator that we're currently using is the NumPy random state, but that most of you. So we can try it out. So we can set some parameter values. So T1 0.1, T2 0.3, and then generate X ops with evaluation of the function, and then we can plot it. Run it. Now, yeah, there's one realization of the MA2 process. So it's a random stochastic time series process. And it's a stochastic process, so it did have the random number generation there. So you can run it multiple times and plot it, so you see that there's going to be some variability in the data points, and that multiple times, then you have idea on what kind of variation it's going to have. So here's the sort of clarification of the batch size arguments. So it's just to speed things up, basically. And if you have a simulator that you sometimes have, that there's just no point in generating a larger batch than batch size 1. For example, in a cancer cell model, it doesn't really make sense. The model is so complicated that you cannot use linear algebra to sort of make many passes of the model. So you always, in our case, in that model, we always have just one realization with one parameter values that we get. And then we have this wrapper tool called ELFI.tools.vectorize that you can use that to sort of wrap that one-dimensional simulator into a simulator that takes in batches. So we can start defining our model. So we have this modeling syntax where we generate the inference models in DAGs. So directed acyclic graphs that you probably saw in the Bayesian workflow presentation, right? I assume so. Yeah. So it's a very clear Lego block type of model building method. So we're going to take our priors, we're going to take our simulators and other pieces of this methods and throw them into a DAG, and that DAG defines on nodes the data goes into the following nodes, and then we always have the sort of the knowledge, and we can be sure that sort of no realizations of random variables left out in the process. So let's generate a empty ELFI model, basically an empty graph called model, because then we start with the prior nodes. Sometimes it would probably make sense to start model building from the simulator node, but because we are dealing with DAGs, so we usually throw in the prior nodes first and then lead them into the simulator node. So there's ELFI.prior class method that constructs a prior node. So we have support for all the Skippy stats distributions. So SS.uniform is the Skippy stats uniform distribution with location 0 and scale 2. So it's a uniform distribution. We give name, the parameter name, as the node name in ELFI, and then we say that this goes into the model that has a name model. And then the second node for the parameter theta2 that we name T2 for short. The same way, we make a uniform distribution for it that has support 0 to 2. So we have, some keywords, so you don't have to make the SS.uniform, because actually it has the exact same amount of characters, the .uniform as SS.uniform, but there you go. Anyways, we name it T2 and say that it's going to go to model called model. Now, then we had our function definition of MA2, and we're going to use the class method simulator. And it takes in the first argument is the function. And then we give the arguments for the simulator in correct order. So it took the T1 and then T2. We give the model nodes as inputs. So the model with a key T1. So most of you probably know Python. So the model graph that we have, the DAG, is actually a dictionary, so you can access the nodes. And the keys are the names of the nodes. Access them in the model graph. You can always access it with key T1 and T2. And we feed them into the simulator. Then we have the observed data that we generated above XOBS, and we feed it to the simulator because that's representative of the simulator. That's our observed data, and that we're going to solve the posterior distribution with. And then we give it a name. So, we're adventurous. We're going to name it MA2. We don't have to give the model equals model this time because it takes the nodes from the model name to model, so it knows that they're going to go into the same graph. So we can run it. And usually when you're building, it's simple here, and it's not that important here when we have very simple model, but if you have very large complicated models with a lot of parameters and lots of bits and pieces, it's usually a good idea when you're building a model to check what's going to look like, because we have the DAG and we can always draw the DAG. So ELFI.draw is the, and it gives our DAG. So it tells us that it takes two nodes, T1 and T2, and they go to the MA2 node. And you don't have to worry about that, why some nodes will appear gray and some nodes will appear white. It's basically, it says that MA2 is a node that we have observed. So we have fed realized data into that node, so it's going to be grayed out. So that's our model, and I guess we're done. Yeah, and other than drawing the models, it's usually a good idea to draw data from it. So somebody asked me about how do you know the thresholds that you should be setting? How do you know the scales of summary statistics that you're choosing? So you may want to every now and then generate data from the model and check what the data looks like before you're starting your modeling. Obviously, basically, there's few things that you can model without, having some information about it. So we have this model, the class method generate from the ELFI graph. So we're gonna, it takes the batches, so it generates one batch with size 1 from the model, and we can tell it to what outputs to get out. So we want to see T1, T2, and MA2 node outputs, and then we can run it. So here's the output format that it generates. It gives a dictionary where under the different keys, so the different nodes, it has a NumPy array of correct batch sizes in it. So our batch size was 1, so it has only one MA2 stochastic process realization under node name MA2, and then from T1 and T2 we generated randomly 2 values basically, and you can draw it. So with these specific values, it gives out this kind of MA2 process. So if we want to compare the simulated sequences to the observed ones, we need to do the summary statistics. So we need to decrease the dimension of these stochastic processes, because I mean, obviously there are metrics. I mean, you could even use Euclidean metric of comparing the stochastic processes that you have generated here. But because of many reasons, there's a problem at if you take the distance between two the stochastic processes, it doesn't tell you, much how close they are to each other, because it happens that like almost all of the stochastic processes are like equally distanced from each other in these high dimensional spaces where there's a lot of randomness there. So we do the summary statistics thing. So because it's a time series model, MA2 model, so pretty often with time series models, you know that you have different kinds of stochastic process summary statistics available. So autocovariances with different lags, for example. I mean, you could add a mean of the process and other stuff there, but we just going to add 2 summary statistics. So so autocovariance with lag 1 and autocovariance with lag 2, and we can add it. So first we define the autocovariance function. So when constructing summary statistics functions, you need to take into account that it's going to be multiple realizations of the data set that goes into the summary statistics. So your batch size can be more than 1. So that's why our output is going to be the realizations of stochastic processes on the rows. So we do that autocovariance for each of the stochastic processes. So each of the rows we calculate autocovariance separately. So the NP-me by different lags, and XS1 tells that it's going to apply this NP-mean on the each of the rows. And the output is going to be then a batch-sized summary statistics. So after we had defined the autocovariance function, we can add them to our ELFI graph. So ELFI.summary is the class method. We give the function as the first parameter, then we give that it takes the output of the MA2 model. Then we give it a name, and because we're adventurous, we're going to give them names S1 and S2. The 2 here is just the option for the autocurrence lag that comes after the X. So this is X in autocode. Then you can draw the graph again when you add something, because what happens, we can actually test it. So if you add a node that you don't tie to the graph, it's still going to come into the model, but it's just not going to have any arrows in the DAG. I don't think we need to demo that. So if there's no arrows coming from your nodes to the correct nodes, then somewhere there was a mistake, and something was missing somewhere. Then, because we're going to do ABC in the beginning, so we need the distance function. So it's a class method, ELFI.distance. We have support for the Skippy spatial distance functions. So the Euclidean distance, for example, we give that, all the summary statistics to it. So it's going to automatically take the realized data, the X-ops that we give to the simulator. When we define simulator, we give it the option X-ops and gave it to realized data. So here, we put it here. So it's going to come to each of the nodes that come after the MA2. So the S1 and S2, they also have the sort of the realized versions that were evaluated with the observed data. So define the distance function, give it the name D. We can draw it. And voila. There's the priors go to the simulator, simulator goes to the summary statistics goes to the distance. And that's it. So now when we evaluate the model, for example, if we want to just draw if we want to use rejection ABC and just generate one value of the graph, what it's going to do is that it's going to generate the first nodes, like the prior values in T1, T2. It's going to pass those random values to MA2, and it's going to generate stochastic observation from MA2. And it's going to pass that along with the observed data to S1 and S2 nodes. And it's going to evaluate those summary statistics with and the randomly generated data, and it's going to pass them to the distance node, and it's going to evaluate them. So it's going to make always full passes of the ELFI graph if you don't tell it that you don't want full passes. So usually the thing is that, you have the access to the Skippy stats distributions, but pretty often you may want to include your custom priors. And we're going to show it first before we do the rejection sampling. So we modify the model a bit. So that's something that you may want to do after you do the inference and the results don't look okay, or you do some generation of the data from using model and it doesn't look okay. You want to modify it. You want to use the Bayesian workflow from earlier this week, and you want to modify your priors because you notice that the priors generated data that looks impossible. So you can modify the prior, so you can keep the same ELFI graph, and you can switch rule of the nodes to other nodes. So we kind of generate the custom priors and switch them for the uniform priors from 0 to 2 that we included in the graph. So first, it's enough that, I mean, the Skippy stats format of the distributions is that it does have some class methods. So it has the certain format. It needs to have the size keyword and random state keyword so that it follows the Skippy stats format. But it also needs to have at minimum, it needs to have a method RVS. And that's the random number generation from the model. And what we're going to do here is that we're going to generate a hierarchical model. So the T1 and T2 are dependent of each other. So we generate a hierarchical model. So the T2 node is going to take a T1 node, and it's going to use T1 value to generate the value from T2. So it's going to be this triangle distribution. So T1 is going to be a Skippy stats uniform random number, uniformly randomly distributed between -b and b. I mean, we're going to set b later on to 2, but then it's going to take the T1 value and it's going to addition the T2 value on T1 so that it's this triangle shape that we're going to demo. Random. So for rejection ABC, you only need the RVS method. But then when you are using SMC ABC or BOLFI or any other surrogate methods that do something with the prior other than draw values from that, you need some other stuff. You need, for example, the PDF or log PDF that you need to define as methods. So you can use the RVS method. And our custom hierarchical prior where T2 depends on T1, it gives output this in this uniform distribution in triangle. So we're going to switch the parameters, the nodes T1 and T2 to these new nodes. So we have the method become. So you can take the node model with the key T1, and it becomes this new ELFI prior that's defined with a custom prior. And then you take the T2 node, and it will become this new ELFI prior that takes in model. And then we can draw it. And especially if you use hierarchical structures in your priors or in other model parts, you can have a hierarchical structure in summary statistics as well. So it's usually a good idea to check the DAG. So it immediately tells you that your hierarchical structure is off if there's a problem there. So otherwise than that, it's the same thing. So evaluate, it takes a pass from top down. Now we can do the first inference method. So rejection ABC, it takes in the distance node. So that's enough. I mean, if we give the distance nodes to the method, it has access to all the other like parent nodes as well. But so if it needs from it, so we define ELFI.rejection object. We give the distance node to it. We give batch size 100. So, I mean, you can run this with different batch sizes. If you put batch size 1, so that it takes like only one random generation of the graph at a time, everything that we're going to do here, you know, you can do, but it's just going to be, you know, much slower. So I recommend using at least batch size 100. Then you can set the seeds and to the methods if you want to ensure that you get reproducible results. So we generate the inference object called reg. Then we say that we want to have 1,000 samples from the approximate posterior with the threshold 0.2 on it. And that's it. We can look at the results. So summary. So in summary, it tells you that it's used rejection method. We wanted to generate 1,000 samples and number of simulations. This many simulations to get thousands samples within threshold 0.2 in the approximate method. And then we get a parameter estimates 0.1 and 0.2 with a 95% credible interval limits. Then you can, plot the results. If you want to use pair plots when you have multidimensional posterior distributions, that's usually So you can see the shape of the distributions wrong with that. And the shape of the posterior distribution, whether or not it looks okay or not. So we can do the same thing for sequential Monte Carlo ABC. Because we had our custom prior, so SMC ABC, it requires not only the random number generation distribution method, so the RVS, but it also requires the PDF, because we need the PDF to estimate the importance sampling weights when we are propagating the posterior samples from the previous round to the next. So, I mean, in this case, when it's just a simple hierarchical model with uniform structures, it's really easy to construct the PDFs. We can run this, and then, because we added something to the node, so we need to make sure that they take effect. So we need to, again, we need to new nodes in the model. And then we can make the SMC object. So give the distance node to it, because it's going to do the inference on the distance node. Batch size, we can keep it 100 and set the seed. So now we have the SMC object. Now we give how many posterior samples we wish to have, so 1,000 samples, and then we get a schedule of thresholds. So it's a decreasing list of thresholds. So we want to run just 3 rounds of SMC ABC, with the first threshold being 0.7, 0.2, the next one, and the final one of 0.05. And we run it with the sample method. So that was pretty fast. And then we can look at the summary of the runs. So it's usually a pretty good idea if you use SMC ABC. First of all, I usually recommend doing SMC ABC over rejection ABC any day, because that's just going to be much more efficient. But then I also recommend looking at the results from each of the populations, from each of the rounds of SMC ABC. You should look at the results, how sort of the performance were. So in the end, we have 1,000 samples with threshold 0.05, and total number of simulations that we had was about 94,500. You could notice that the number of simulations is always going to be a factor of batch size. So we asked 100, so it's always going to be divisible by hundreds, the number of simulations. So if you would ask a batch size of 1,000, it would be probably about 94,000. And then for each of the populations, we start with the population 0. So this was the first population. We asked for 0.7, we got threshold about 0.68. 1,000 samples required 2,800 simulations, and so the means for T1 and T2 are whatever they are, and the credible interval is pretty large, which is expected because the threshold is so large. And then if you look at the other populations, you see that the credible interval starts decreasing, and the mean starts settling in closer to the final sample means. So you may notice that here that in the final round, it took about 75,200 to get to 0.05. So sort of the bulk of all the simulations were carried out in the final round to get to the within threshold 0.05 from threshold 0.2. And you can look at the marginals to see idea of what the credible intervals look like with different populations. So they decrease, pretty quickly. The final population. So that it's a Pythonian indexing. So population 2 is the results from the third round. Okay, and now we SMC ABC, the total number of simulations was about 94,500 to get within threshold 0.05. Just to demo how much more efficient that is with SMC than Jackson ABC, we can ask 1,000 samples from Jackson ABC by asking the same threshold 0.05, and if we run it, takes a while, so you can guess that it's going to be a large number. Spoiler result is already there, but so without having the importer sampling step, like gradually getting the estimate better, we require about 500,000 simulations prior to get within this threshold. So, SMC ABC is usually much more efficient than the rejection ABC, unless you have very sort of tight and prior information about the parameters, obviously. But, then you probably wouldn't need to do the inference anyways. Okay, so rejection ABC and SMC ABC, the basic usage of those is pretty simple. You have different options. You can use the quantile option as well with both rejection ABC and SMC ABC. So you can ask from rejection ABC for 1,000 samples and say that, quantile 0.01, then it's gonna, make 100,000 simulations and keep 1% of these, so 1,000 simulations. So if you want to fix the computational resources, you can use the quantile approach as well. But then let's demo ELFI. So it's a bit more involved, it has more moving pieces. So the ELFI uses the Gaussian process in our case. It's the GPy, so GPy package that we're currently employing, fitting the Gaussian process. So everything is the same. So for all of the methods that you feed, like you can feed the same ELFI graphs to all the methods. The only thing that you have to keep track is that different methods may use different end nodes, for example. So you could do synthetic likelihood with the same ELFI graphs, but synthetic likelihood wouldn't have any need for the discrepancy function. So for a synthetic likelihood type of method, you would feed probably just the summary statistics nodes instead of the discrepancy node. So same graphs, but use different nodes. That's the idea in ELFI. And for the Gaussian process fitting, the one thing that I didn't mention in the introduction slides is that when fitting GP to the distance nodes, is that sort of pretty often it makes sense to take the log transformation from that. Because if you distance metrics naturally can be a bit right-hand side tailed. Just if you think about chi-square distribution and how it's defined, it's the same with all distance metrics, so they can have long tails. So you may want to take the logarithm transform. The other reason is that it may not make sense to fit a Gaussian process to a distance node that that is going to be bounded below by 0. But the Gaussian process obviously is not bounded below by 0. So Gaussian process gives non-zero probability for negative discrepancies. So, but that's not a problem if you have transformed the distance nodes with the log transformation. So we have gone over the prior nodes, the simulated nodes, summary statistics nodes, and distance nodes. But there are other nodes in ELFI. One of them is operation node. So basically, it's just a wrapper for making new nodes that are defined by deterministic transformations. So we can take the distance node model key D and give it numpy.log and give its name -d, run it. Now we should find it in the model. Yeah, it's there. So now we can define we can construct the ELFI object with different options. So our response is going to be the final node, which is the log transformed discrepancy node. You don't have to do a log transformation to the discrepancy node, no, but you can. I usually do it. So it takes the final node as the first key. Then we use batch size 1 in ELFI. And does anyone have a good idea why we would use batch size 1 with ELFI? That's an active learning based method. So it's because like with each of the passes, evaluations of the graph, we'd want to find a better parameter value where to sample. So if you sample hundreds sized batch at one location, it doesn't really make sense because you want to minimize the number of evaluations. So if we estimate only one parameter value, then try to find the next best one, and after that the single best one, and after that the single best one, you minimize the total number of simulations to get the most informative evidence. So initial evidence is, before we start doing active learning, we fit the initial GP to the data, and in initial evidence, either it can be data set that you have gotten from somewhere, or it can be an integer number which basically says that this many generations from the prior we're going to generate, and then we're going to fit the initial GP to that, and after that only we start doing the active learning and trying to find where to query the simulator next. Update interval is the interval how often we're gonna optimize the hyperparameters of GP. Bounds are for GP and also for the Bayesian optimization, so that we are only looking at that region. when fitting the GP. And then acquisition noise variances, they balance the exploration, exploitation, the acquisition function, which by default is the LCB. Struck it. And we can run it. So, because the ABC, SMC, ABC, and rejection ABC, they both use the sample method to draw directly the samples from the posterior distribution, but ELFI is going to have one method in the middle that's the fits of the surrogate before we do the sampling. So we fit the surrogate posterior. It shouldn't take too long, but so demoing the power of ELFI is kind of silly with the simulator that you can draw 500,000 points in 5 seconds, because the Bayesian optimization part takes about, I don't know, what, 30 seconds? But anyways, you just have to you go to a mind palace and think that the simulators, each of the queries will take about, I don't know, 18 minutes. So that it makes sense. And now the GP has been fit. We can look at the target model. It's still currently in ELFI. It's named target model. That most likely is going to change in the next release of ELFI. Anyways, so it's kind of prints out of the properties of the GP. That's how many parameters you had and so, and you can look at the values, and you will probably see here if something was like way off in the GP fit. But you can obviously also draw it. The block GP method. And it's by default, it gives this pair plot. And because the contour is it's from the two-dimensional GP, so it's been conditioned on the minimum value, or the value where the minimum was button. That's the slice in the contour. But you can see that quite a few of the points are around 0 here. And here they concentrate at about 0.5. So you get a estimate of the posterior without having to do 500,000 evaluations of it. But then you can do much, much better using different acquisition methods. So we can use the maximum variance acquisition method. The API for doing that is that you need to define this acquisition object. So it takes the acquisition base class, it takes in our surrogate type, which is GP at this time, and the prior as well. And then it goes into the ELFI object constructor, and when you do it, you can run it. It's going to take hopefully not that much. Oh, I allowed errors. And no. 27 seconds. It was actually less than for LCBSC. So here you can see that the LCBSC was doing way too much of exploration of the parameter space compared to the maximum variance. So it really put a lot of points, the maximum variance acquisition method, where the bulk of the points should be going to. So if you look at the distribution acquisition points, they are pretty spot on. And the other thing is that the LCBSC as an acquisition method doesn't use the prior information at all. So the sort of the evaluation points can be basically anywhere where you're fitting the GP in. But here with the maximum variance method, you'll find acquisition points only in the prior region, and it's quite more efficient than LCBSC. Then you can run this. I don't think we're going to run the expected integrated variance, but actually we're going to run that instead of randomized maximum variance. So randomized maximum variance is going to be better than maxvar, and then we're going to have the final method. So when computing the expected integrated variance and randomized maximum variance method, they both need to calculate the important sampling distributions. So they have, within finding where to evaluate next, they have to calculate the intervals in them. And we calculate them intervals by samplers. So we do a metropolis, so MC sampling. Each round we select a next query point. And here in simple problems, it's probably a good idea to use metropolis sampler and give secret proposals for it instead of nuts, because that would be nuts and also very slow. So if we run this, we will hopefully get even better results. It's just a runtime warning usually. Here, when choosing the point where to evaluate the acquisition function next, nut sampler would be a good idea when you would have a complicated distribution. But that's much less, I mean, it's much slower than metropolis. And this is only for choosing where to evaluate the next point. So we can deal with having a metropolis that's probably not as accurate because it's just for the selecting the next point. After 25 minutes, I'm going to stop this. So the sort of the fancy acquisition methods that they really only make sense simulators that are expensive, or you have sort of in a sweet spot of dimensionality that you can use these methods. Not that low. Yeah, looks good. So you can see, I mean, compared to the LCBSC, the fancier methods, they are much more efficient on selecting the points, but they are much slower also to sort of to execute. So just the final thing on getting you on track on finding posterior distributions is that when you are using ELFI or any of the other surrogates fitting methods that we don't have in ELFI yet, but you can probably find in Zoors, is that when you have your surrogates posterior distribution, you still need to sample from it. So, basically everything you do in Bayesian statistics is going to be based on samples from the posterior distribution, because with those you can calculate whatever you want. You can, expected values of any function. So we need to draw a sample, so use the same kind of sample method that we used in rejection ABC. So for here, we're going to use the nut sampler, but we're going to just show like 200 samples from the posterior distribution, because it's not that time consuming in this case, but it could be. So the nut sampler is the default sampler for the ELFI circuit fits, but you can use other samplers as well, Metropolis or something. The default is that it's going to run 4 chains, and the default also is that it's going to throw out half of the values as a warm up or the stage samples. And we are done. And you can sampling results here. So it's going to give you a effective sample size and R hat, that's a convergence diagnostic. So effective sample size represents roughly how many independent samples you would have in the posterior distribution. And also R hat tells that whether or not the method has converged or not. So it should be less than 1.1 as a rule of thumb, so that you know that you have converged. But I also recommend on looking at the trace plots as well, because they give you an idea if there's a problem there. So the summary method works, so you can find the mean and the credible intervals, and to plot traces gives you for both of the parameters T1 and T2 the trace plot for all of the chains. That's the sound of the brake, but so if there's a convergence problems, you can probably see that in the trace plot. So the sampler can plateau in some parts of the space, and that's probably problematic. And it also gives you an indication whether or not you should run your sampler longer. With 200 samples, well, I just eyeballing it, they're fine. If you want to do it faster, you can also use the Metropolis sampler with, and you need to give the sigma proposals, so the proposal density variances for each of the parameter dimensions separately. But you can draw quite quickly about like 2,000 samples from it. So you have a larger set of samples. Nuts. But definitely there's going to be a geometries in the posterior distribution where Metropolis is just poor compared to nut sampler. Well, for example, here's a case where it didn't go well. 4 chains of 2,000 iterations, effective sample size 12, convergence diagnostics 1.4, 1.2. So we can plot the traces and probably see that something is off. Yeah. So you can see that the sampler had gotten stuck. I think the problem is that it's probably gotten stuck because we have a triangle region. It's probably in the corner, right? Because, you go randomly in random directions using a Gaussian proposal, and it just don't get out from the corner that has a angle that's less than 90 degrees. So that was a nice demo. Okay, so we could have the 10-minute break now. then anyone who wants to start working on the assignments, maybe you have already started, some of you, then you can come back in 10 minutes and you start working on that. Ask questions. You can ask on the Slack, and every like 10 minutes, we're going to go through one step ahead, and then you can work on the next part of the problem. So that in the end, by 4 o'clock, everybody will be in the end about.